Hello, everyone, and welcome to the second part of this lecture. Um, Last time, before we ended, we were discussing this scenario of a future smart grid, and we showed how a distributed generation scenario, aided by the possibility of electricity storage devices at the user side, can actually enable a huge change and transformation in how current power grids work. And it can actually enable the full self-sufficiency and full sustainability of our energy systems. We also showed that small communities labeled as microgrids can be formed that help each other and work in self-sufficiency mode. And this is what we actually want to achieve in the future. After that, we must talk about the two parts constituting a smart grid. Now, the first part is the transmission network. So far, we have discussed different scenarios and solutions to be deployed at the distribution side, so at the user side. And we did not really talk about the transmission network itself. Now, the transmission network is a very important role, has a very important role in the power grid because it is the biggest part of the power grid. So you have a nationwide critical infrastructure that runs for miles, and this incredibly big infrastructure is very high maintenance. So it costs a lot to build new infrastructure, so to build new power lines or to build new power generation factories. And at the same time, it includes a huge risk because building these factories is full of risk. Maintaining these factories and maintaining the power lines is also full of risk. Now, there's a high impact of failures on the power grid that can result in blackouts of entire cities. So it's actually a very critical part of the power grid. So when you think of a blackout, yes, at home we can have a blackout and have candles, so that's not a problem. But if you have a blackout at a hospital where major systems, health critical systems are shut down, then you have a problem. When it comes to law enforcement, you have a problem. When it comes to airports, you have a problem. Yes, all of these sites will have secondary power generators that they can rely on at this time. But when a failure happens, you don't have an expected, so you don't know how long it will affect this part of the grid, and therefore you would like to avoid that at all costs. Now, the infrastructure itself is spread over a huge distance, so it's a very wide area network. And this transmission network itself is extremely subject to change. So if you have solar fields, you need to change the direction. So these PV panels must change their tilts depending on where the sun is. It also needs to change the direction they're pointing at depending on the time of the year it is. When you have onshore and offshore wind farms, they change depending on the season. So you might have to predict how much energy or how much power you're generating at a certain day, depending on the previous days of the year. It also is extremely subject to change because you need to employ more energy storage units depending on the time of the year. So, for example, if you're in the summer, you're generating more solar power, so you need to use more energy storage to store the excess power you're generating. So, having said that, this plot shows us the expected storage needed. So you have here the green is the pumped storage hydropower. So this is the way you store energy. So you actually use the excess power you generated in order to to transform this into stored hydropower that once released, they will spin turbines and generate power. And on the blue side here, this shows you the storage that you need by 2030 to actually satisfy the excess power generated. Right now, there is a division of different sides of power storage. So you have, first of all, sodium-based batteries. You have flow batteries. You have lithium-ion batteries, which is the one of the most healthiest types of storage units. And you have, of course, compressed air storage. And the problem with compressed air storage is that it's not exactly that efficient. So you have an efficiency factor that you multiply it by it. And it's also extremely expensive. So the share of the annual battery storage additions, depending on the different technologies they use, so whether they use batteries, they use compressed air, or old style batteries that are lead-based, we can actually see that the amount of lead-based batteries being used diminishes over time, and that is for environmental purposes, that these lead-based batteries lay huge waste to the environment. So you see that the amount of lithium-ion batteries increases and the amount of lead-based batteries decreases. All right, so we've talked about the integration of storage systems and their importance in the power grid. Now, the table that we have here discusses completely two different parts of the grid. So we have on the left side the transmission network, and we have on the right side the distribution network. Now, let's talk first about the transmission network. The transmission network requires an incredibly high level of control. So you have extremely high voltages running through these power lines, and you want to control them at every point in time. You need to know the amount of power you're transferring to a certain part of the city and the amount of power you're transferring to another part of the city. So at any given time, there is complete control over the power lines and over the grid, right? The transmission network itself is spread over a very wide area, mostly rural areas, so there's not a lot of users in place, which means that you have low density of devices. So you can have power lines running for hundreds of kilometers without reaching a transformer or without reaching a repeater. There are monitoring systems already in place in order to have the aforementioned high level of control. You have extremely well-established standards that are agreed upon across continents. So Europe uses the same standards all over. The US uses the same standards all over. And this creates this synchronization between countries that enables also the exportation and importation of power. You are dealing with very, very high voltages, which means that there is a high level of risk when dealing in maintenance or construction. And the renewable-based power plants are less volatile because, as we said, you use energy storage systems that kind of optimize the power plants and tackle the challenges with volatility of the renewable-based generation. Right. So this is a very controlled environment, very architecture based. They're constructed for a reason. They have standards. Everything is well defined, right? And then we look at a completely different scenario, the distribution network. And this is like where the chaos happens. You don't have that high level of control because inside a user's home, you have privacy. So you don't know what he's using, what kind of electric machines that he has at home, or if you're operating a factory, you don't know the types of machinery that are operating inside, right? So you don't have the same complete control over your network anymore. You have different scenarios. You can have households, you can have shops, you can have factories, you can have charging stations, you can have campuses that are home to laboratories. So you can have completely different scenarios that you don't have always the complete control over how the scenario is designed, over how the internal power grid inside a home or a factory is designed. This is completely up to the user, right? And having said that, because it's up to the user, different parts of the distribution network is deployed in different times. So even if you go out of the user space, even if you go into the distribution network itself in the street, different parts of the city, different parts of the distribution network are developed over time. So some parts of the infrastructure might be very up-to-date, parts of the infrastructure might be old, and still uses copper wires. So, for example, if you take the communication infrastructure, which is similar to the electrical infrastructure, you can actually see that there are parts of the city where you can have fiber optic cables. So you can have very high speed internet, while in other parts of the city you don't, because the underlying infrastructure is actually not capable of providing high speeds. And this is similar to the distribution network of the power grid. Now, you also have cheap thin cables running inside the homes because users might need to reduce cost of the power grid they construct inside their homes. So you might have very high losses in terms of the dissipated energy in the cables. You also have a high density of devices, which it needs monitoring in a different way than in the transmission network that has a very low density of devices, because you need, which we'll talk about later as well, you need a very high density sensing environment in order to be able to provide accurate control over these devices. You don't have a standard for remote controlling this distribution network. So you have some standards on how the distribution network itself is built, but you don't have standards on control. So let's take a simple example of smart homes, right? So me at home, for example, I use Apple Home, so the Apple Home Kit. And this means that I need to look for devices that are compatible with Apple Home. Now, this limits my choices because not every device is compatible with Apple. However, if you use a different remote control platform, such as Google Home, for example, or like the brand that is written on the devices would be compatible with Alexa Home, it means that, or Google Assistant, it means that you have different types of devices that you might be shopping for in order to be compatible with that. So there is no standard way, there's no standard platform for home automation. So you can reflect that also on the bigger things, on managing an entire building. There are different companies offering different energy management systems for buildings, for companies, for factories, and there's no one unified standard. Even the remote meter reading itself is not deployed everywhere. Right now in Germany, it has been standardized, and a lot of companies are replacing the old meters to remote meter readings. But even when you do have remote meters, you still need to be within a reading distance. So they need to still go to the building, stand in front of your door and read it wirelessly. So they don't need to go inside your home, which is in itself a big advantage. But they still need to go on site and read it manually. So this is still not exactly where we want it to be. We still want to go this extra step of reading it completely remotely. And we will talk about that also when we discuss the ICT side of the smart grid. Good. So having discussed the two different approaches, what are the main challenges of transmission networks? So the transmission network, being a very high risk environment, needs very reliable monitoring systems and very accurate controls. It's spread over an insanely wide area, so these monitoring and control systems need to be also compatible with these extremely large distances. However, these monitoring and control systems are extremely complicated. So even if you want to build this control system, this remote monitoring system, you have different entities responsible for different parts of the transmission network. And in order to identify all the possible risks or disturbances in the transmission network, you need to obtain information from different sources. So in the table here, we have different types of information that you need to actually get in order to be able to correctly control and monitor your transmission network. So, for example, here you have generation plans according to the Renewable Energy Sources Act. So here you have to monitor the power generated in renewable-based plants, right? And these alone provide different types of information. You provide the installed capacity, which means that when you constructed the power plant itself, you made it with a maximum capacity of a certain value. The available capacity of these generation plants, which means that the available capacity at a certain time, or this available capacity changes over time depending on the depreciation of the power plant itself. So it does not operate at maximum capacity the whole time. The maximum capacity reduces over time. And the forecast or the predicted generated renewable energy that you can actually generate at a certain time, which is updated daily. And this is only about the renewable power plants. So when you go to the coal plants, again, you have the maximum capacities, and then you have also the expected generation of a certain plant. You have to monitor the imports and exports coming in and going out of the country. Then you have to monitor the load, which means that you need to also be able to monitor your distribution network and gather data about the aggregate power demand of a city, of a certain part of the network. So when you look at this table, you have a very large amount of information that you need to put together, and you need to monitor all these parts simultaneously and then control it at the same time. So what is the role of ICT here? How can we actually be able to monitor every single part of these different types of information? How can we process this information? How we can make decisions based on these information? This is where ICT comes in. This is where information and communication technologies come in. So here, first of all, what do we have to monitor? What do we have to sense? So to answer that first question, we go back to this table. From this table, we see that we have to sense the wind power, for example, in order to be able to predict the wind energy that we can generate at a certain day. Same goes for solar energy. We need to be able to sense the solar power. In order to monitor the imports and exports, we need to be able to monitor the power lines at the borders, right? So we need to sense the line-to-line power or currents. To monitor the loads, we need to have remote infrastructure sensing the transmission lines or the power lines at the user side in order to aggregate the entire power demand of a city or of a certain area. So when we go here and we see that at the very beginning phase of this monitoring system, is the sensors. So you have at the power lines, for example, at the borders, you can monitor the conductor temperature sensor, so the temperature of the lines. You need to monitor the tilt of the towers. You need to monitor the formation of ice, for example, in order to avoid fire hazards or short circuit faults. So that's only one part. So that's only in the transmission lines. So when you actually talk about a remote infrastructure, we're talking about thousands of sensors monitoring different phenomena, different parts of the grid. And all of these sensors must send their data back to a place where this data can be processed, can be stored, and can be used to make a decision in order to make a control decision that changes the grid somehow. So the second question is, how frequently do we have to sense it? So some of these phenomena can be sensed yearly, can be sensed daily, or some of these phenomena must be actually sensed every 1 minute, every 30 seconds, or even every 1 second. The third question is, what kind of technology offers the desired coverage? So when we're talking about the transmission network, we're talking about distances of over more than 100 kilometers. So is it possible to provide this kind of coverage with wired cables? But what kind of wires? Do we use copper wires? There would be a lot of cost for these wires, plus the maintenance overhead, plus the fact that you actually need to deploy them, right? And with an extremely large distance network, it might not be very practical to lay wires for hundreds of kilometers. Okay, what other types of wired cables do we have? Optical fibers? Well, that's even more cost, and you don't need very high speeds or very high data rates in order to send a 8-bit reading every couple of hours, right? So it doesn't make a lot of sense to use wired infrastructure. The second option you have is using wireless infrastructure. So what infrastructure? So what spectrum, which frequency do we use? What kind of technology do we use? Do we use Wi-Fi? Is Wi-Fi able to use that? Do we use the cellular network? Are we able to use that? We're going to talk about all of that during the next 2 lectures. How much data are we going to be dealing with? Is it in bits, kilobits, megabytes, gigabytes? What's the price of failure? So you can have short circuit faults that create blackouts in entire cities. So the cost of failure is actually pretty high. So these systems must be extremely reliable. So the readings must be reliable, the communication side must be reliable in order to give commands, and how fast these commands, how fast are the readings must be transferred or transmitted, and how fast do the commands need to apply. So in the standards, for example, the time between detecting a short circuit fault and so the time between detecting a short circuit fault and isolating this part of the grid that has a short circuit fault in it must be no more than 30 milliseconds. So that means that you need to sense the short circuit fault, send the information back to the central processor or the cloud or your application, and then detect the fault, send back the command to isolate the network, and all of this round trip must be less than 30 milliseconds. So this needs extremely fast communication. And the last question is, how secure should it be? So if you have an unsecure communication channel, then somebody can actually hack it and cut down the power over an entire city, which is not very attractive. All right. Then when we talk about the communication side of the control systems, then we need to first introduce the different frequencies that you can work with. Most of these frequencies you know from the radio, right? The VHF, the UHF, you know from the, or even the MF, which is the AM. So this you know from radios, right? But under that, you have the extremely low frequencies. So this is communication with submarines in the range of hertz or hundreds of hertz. So that's extremely low frequencies and super low frequencies. Then you have the ultra low frequency, which are for communication with mines. Then you have the very low frequencies. There you start going into the kilohertz spectrum with navigation. So this is more about navigation, wireless heart rate monitors, or geology devices. Then you have the low frequencies, which goes into the hundreds of kilohertz. And this is the AM long wave broadcasting. So this is what you get on your radio or your RFID when you, so these small RFIDs that you have in your Mensa cards, for example, that you can use to pay contactless. You have the middle frequency, which is the AM medium wave broadcasts. Then you have the high frequencies that start going into the megahertz, which are citizens band radio, so amateur radio. You can use these bands for yourself. You can have the near vertical incidence skywave radio communications, the marine and mobile radio telephony, so for boats and marine radios. Then you have the very high frequency that goes into the megahertz, so from 30 to 300 megahertz. So this one is mainly a FM, so you have that on your radio as well. You have television broadcasts on that, line of sight ground to aircraft or aircraft to aircraft communications, so how they communicate with planes. And again, with amateur radio and weather radio. Then you have the ultra high frequencies, which you go into thousands of megahertz. You have also television broadcasts, you have microwave oven, microwave devices, and this ultra high frequency is where most of the wireless technologies operate. So one thing you actually might not know is that the same band where your wireless LAN at home or your Wi-Fi works is actually the same band as your microwave oven. So your microwave oven, when it's on, it actually interferes with your Wi-Fi. However, it's not that creates an interference for a couple of meters. It's just a couple of centimeters. So in that band, you also have different Internet of Things technologies. We're going to talk about that in more details in the next lecture. And you have satellite radio and remote control systems. Next, you have super high frequencies that goes into the gigahertz, so from 3 to 30 gigahertz, where you have also certain bands of Wi-Fi. So this is the high frequency Wi-Fi. You also cable and satellite television broadcasting and satellite radio. Then you have extremely high frequencies that start going into radio astronomy, directed energy weapons, so lasers, or millimeter wave scanners. Then you have terahertz frequencies, which are mainly for physics people that are for ultra-fast molecular dynamics or experimental medical imaging to replace X-rays, for example. So these are the different bands, and most of our applications in smart grids will be lying in the ultra-high frequencies. So in the 2.4 gigahertz to be exactly. So having talked about the transmission network before, let's now talk about the distribution network. So we said that the distribution network needs a change in how it's operated in order to accommodate the energy generated at the user side. And this requires that the power flow itself becomes bidirectional instead of being going in the same direction from the utility company to the user. And the grid itself has been designed to be a one-directional power flow grid, and therefore we need to change that. And this is one of the main challenges, right? So it's not going to be easy to deploy bidirectional transformers in all parts of the grid, but I think that in order to actually make this transition into a self-sufficient, into a sustainable, completely sustainable energy system, we need to make this change. Now, one of the challenges of the distribution network is the rising power demand. So we are relying more and more every day on electricity to power our increasingly user equipment addiction. So we're powering on our phones every day in the morning, or we're charging them multiple times during the day. So there is an increasing power demand that needs to be accommodated. We have a fast-changing environment in the sense that you have a ecosystem that is changing over time, where people can generate power at home that they can rely on, and the power companies or the utility companies cannot stay in their old school tradition of thinking and ignore that fact. So the environment, the ecosystem of energy is changing, and everybody has to adapt to it. That's why there is a lot of startups that are currently working on the problems of smart grid management, together with customers, so with clients, with users, and with utility companies, in order to revolutionize the distribution network. You have a very high volatile, highly distributed local generation, so you cannot, as a utility company, you cannot actually rely on the generation at the user side, because of the volatile nature of the renewable-based energy generation, and also because you cannot put that kind of pressure on the user side. You need to actually acknowledge the presence of small energy storage devices in order to be able to use them to your own advantage. And this is a challenge because you need to monitor these energy storage devices. You need to know the state of charge at given times during the day in order to decide whether or not to use them. You have electric vehicles that come and go. They are suddenly in need of charging, so you need to accommodate them when they need to charge, and they might be used as well as storage devices, so you need to also have this kind of ability to know when to charge and when to discharge. One of the biggest challenges, in my opinion, is the protection right now. So the protection side of the distribution network is based on fuse boxes. So the way these fuse boxes work is like any other fuse box. It measures the current passing in one direction, and if this current is higher than a certain threshold for a certain amount of time, then the fuse drops and you are isolated from the grid. However, right now, if you have a bidirectional movement of power flow, then when two currents are going in the opposite direction, they will reduce each other. So at the fuse box, what you're actually measuring in one direction is the sum or the aggregate, let's call it that, of the two directions of the two currents moving in opposite directions. So, for example, if you are at a certain fuse box, if you have one line pushing in 100 ampere and one line pushing in the opposite direction 20 ampere, then the resultant will be 80 ampere. Therefore, it might actually be very dangerous for the distribution network if these fuse boxes cannot detect short circuit currents anymore, so they don't detect the faults in the network because of this change in the power flow. And therefore, you need more intelligent ways to detect a fault that is based on monitoring the individual power lines and not monitoring or not measuring it based on the traditional fuse box threshold current way. Then you have the last challenge, which is the extreme heterogeneity of the loads in the power grid. You have loads that create very narrow peaks. So, for example, your washing machine is not constantly demanding the same amount of power, but it actually has these peaks. So whenever your centrifuge is spinning, it's demanding power, and then it relaxes, and then it demands power. So you have, if you look at the power demand of a washing machine, you have these peaks of power demand. And on the other hand, if you use your kettle, you actually have a constant line of power demand until the water is heated. So different loads require different types of different loads result in different power demand profiles, and therefore they also result in a different way to satisfy them. Well, you need to guarantee the stability of your grid despite of the volatile generation. And as we discussed before, you can guarantee that with distributed battery systems, but you cannot rely on the user to do that. So you as a utility company or as a smart grid management platform, you need to be able to provide that with a certain level of certainty. You need to control your energy demand, which is a very big challenge because of privacy concerns. So you need to shift the loads in a way to avoid peaks in the power demand. And it's very unlikely that you will talk to a user and tell them you need to schedule your laundry at a certain time of the day in order to shave the demand peaks, right? But if you have automatic controllers for homes that kind of do that automatically and optimize the user usage in order to create economic gain for the user, then it would also be attractive for the user to use it. And because we want to provide some kind of value for the user to use these energy demand shift or load shift, then we need to provide a optimization on cost. So one of the things that motivate users to use new technologies or to actually give up their privacy in a way is the economic profit. So if your systems optimize cost, then it would be attractive for users to use. And the reason why we want to do that is because when we have a high disparity between load and generation capacity, then we increase the generation capacity of the non-renewable sources in order to satisfy these peaks in demand, and therefore we increase also the CO2 emissions. So in order to reduce the carbon dioxide emissions, we need to actually be able to control the demand and have it satisfied with the available renewable energy capacity and with the help of the distributed energy storage systems in place. As we said before, you need to have a fast recognition of failures And you can only do that, as we mentioned, by having a very high communication system, a very high speed communication systems in place. You need to also have a very sophisticated forecasting model of both generation and consumption, or production and consumption. And you need to embed it on a very large deregulated market. So the power market itself is extremely large. You can have day-ahead trading, so you have the expectation of the energy prices for the next day, or the expectation for the power demand profile of the user side of the next day, but it will not be very certain. It will not be completely accurate. So you have to create your forecasting models based on predictions, and you need to also adapt it to be able to accommodate the inaccuracies in these prediction models. One of the things that you also need to do is to do in-house optimization management. So you need to create these algorithms or platforms that are some of the startups in the energy ecosystem right now are doing, which is create these algorithms that optimize the usage of power inside your home. So they tell you when to shift your loads, when to use certain electricity equipments in order to have a constant power demand profile. So again, what is the role of ICT here? We mentioned before that in order to solve some of the challenges in the transmission network and in the distribution network, you need a very high speed communication system to first accommodate the latency requirements that you need. So you have you need a fast reaction to faults in order to isolate certain parts of the network. You need also a very fast transmission of control signals in order to turn on or turn off electrical equipments. And you also need a reliable remote infrastructure system that can span between hundreds of miles if we're talking about the transmission network, or hundreds of meters when we're talking about the distribution network. Let's stop here for this part of the lecture, and I will see you guys in the next part.